Hey everyone, and welcome to our crash course on the foundations of water treatments. We're going to pull back the curtain on how we take raw, murky water and turn it into something clean and safe. It's an awesome journey of physics, chemistry, and some really clever engineering, all driven by one single fundamental mission.
So, to really get why this is all so important, you have to wrap your head around this chart. A wild 96.5% of all water on Earth is salt water in the oceans. That leaves this tiny, tiny sliver of fresh water. And most of that is locked away in glaciers. I mean, that's the reality we're working with. This incredible scarcity is why every single drop counts. And it's why the process we're about to walk through is just so vital.
And this right here, this is the core of it all. This is our prime directive. See, our job isn't just about getting the dirt out. It's about making absolutely sure that when we're done with it, this water is safe for you to drink and safe to return to the environment. That is a massive responsibility.
Okay, so here's our game plan for today. We'll kick things off by understanding our responsibility as engineers. Then we gotta measure the water coming in. After that, we'll get into the first physical and chemical hurdles we throw in the water's path to kickstart the whole cleaning process.
All right, first things first. Before we can even think about designing a pipe or a tank, we have to nail down two basic questions. Who are we treating this water for, and what exactly are we trying to pull out of it?
When you look at the water flowing into our cities, it breaks down kind of like this. About 40% goes to our homes, 35% to businesses, and the rest to things like parks, firefighting, and, leaks. But here's the real kicker. All of that put together is just a drop in the bucket compared to agriculture. Farming alone uses a staggering 70% of all our fresh water.
So, what stuff are we actually removing? Well, think of it in three sizes. First, you've got suspended solids. This is like sand in a glass of water. You can see it, and if you wait long enough, it'll settle. Then there's colloidal particles. Think of milk. The little bits are so tiny they just hang there, making the water cloudy. And finally, dissolved stuff, like salt in water. It's basically part of the water itself. For today, we are laser focused on getting rid of those first two, the sand and the milk. Now, you can't treat what you don't measure. Before anything else happens, we need one absolutely critical number, the flow rate. How much water is coming into our plant every second? That single value dictates every single design choice we make from here on out. So how do we get that number? Well, we have two main tools in our belt. If the water's in a pressurized pipe, we use a Venturi meter. Just imagine pinching a garden hose. Where you pinch it, the water speeds up and the pressure drops, right? A Venturi meter does exactly that, but in a very precise way. We measure that pressure drop, and bam, we know the flow. Now, for an open channel, like a big canal, we use a Parshall flume. It's basically a specially shaped ramp that lets us figure out the flow with a lot less fuss. All right, we know our flow rate. The water is now officially entering the plant, and its treatment journey begins. First up, preliminary treatment. This is where we use simple, kind of brute force methods to get rid of all the big, obvious junk. You know, the first method is actually surprisingly simple. Just let the water sit. Seriously, in a big reservoir, time and sunlight do a ton of the work for us. In about a week, most of the heavy stuff settles out, and the sun's UV rays can kill off up to 90% of harmful pathogens. After that, it's on to screening, which is exactly what it sounds like. We run the water through a big screen to catch all the leaves, branches, and other large debris. But even a simple screen has a critical design role. It's all about velocity. If the water blasts through those screen openings too fast, we're talking more than a meter per second, it'll either just push the debris right through, or it'll plaster it so hard against the screen that you can't get it off. So a huge part of the design is making that screen big enough so the water can flow through nice and easy. Okay, the big stuff is gone. Now we have to deal with the smaller, suspended particles, the stuff that makes water look murky. And for this part of the job, we call on our most powerful, totally free, and 100% reliable friend, gravity. This all happens in a huge tank called a sedimentation basin. And designing one of these is a real balancing act between three things. First is the detention period. That's just how long we let the water hang out in the tank. Second is the surface overflow rate. Think of this as a race. The particles trying to settle down while the water is flowing up towards the exit. If the particle can't fall faster than the water is rising, it gets washed away. And third, there's the weir overflow rate, which just makes sure the clean water flows out smoothly at the end. And inside that massive tank, there's one more crucial speed limit we have to obey: scour velocity. If the water moves sideways too fast, it acts like a broom, sweeping right across the bottom and stirring up all the gunk we just worked so hard to settle out. It would undo everything. So the whole tank is designed to keep the water moving slow and steady.
So gravity's done its job on all the heavy particles. But now we face a much sneakier opponent, those tiny colloidal particles, the ones that make water cloudy and just refuse to settle down. To beat them, we have to switch gears from physics to chemistry.
So why won't these things just settle? Well, it's because every single one of them is carrying a small negative electrical charge. And just like trying to push two negative ends of a magnet together, they constantly repel each other. They push each other apart so they can never clump together and get heavy enough to sink. You could say they're stuck in a permanent state of social distancing.
The solution is this awesome two-part process, and it starts with coagulation. We add a chemical, like alum, that forms positively charged particles in the water. Then we mix it in really, really fast. These new positive particles go around and neutralize the negative charges on the colloids, breaking down that force field that was keeping them apart.
And that brings us to step 2, flocculation. Now that the particles aren't repelling each other anymore, we switch from that super fast mixing to a slow, gentle stir. This is like the slow dance after the party. It encourages all those little destabilized particles to gently bump into each other and stick together, forming these bigger, heavier clumps we call floc. And these are finally heavy enough for gravity to grab hold of.
So how do we know if we're stirring just right? Well, engineers have a magic number we aim for, called the GEAT value. G is basically the intensity of the mixing, and T is how long we mix for. See, it's a trade-off. You can mix really hard for a short time, or more gently for a longer time. The goal is to hit a total mixing dose right in that sweet spot between 30,000 and 60,000. That's what creates the perfect floc.
All right, let's just pause for a second and recap our journey. We started with our core mission. We figured out how to accurately measure the water coming in. We used simple screens to get rid of the big stuff. Then we let gravity do its thing in sedimentation tanks. And finally, we used that chemical 1-2 punch of coagulation and flocculation to take care of those stubborn little colloids.
The water is looking a whole lot clearer now, right? We've removed the things we can see, and even the tiny things that make water cloudy. But, the most dangerous threats are often the ones that are invisible. What about the dissolved chemicals, the viruses, the bacteria? What about the threats we can't see? Well, that's exactly what we're going to tackle in our next explainer.